Hi there. Let me go ahead and start my video. So welcome, this is Melissa Whitmer, and I'm going to be hosting a live review tonight for the Chapter 6 quiz in college algebra on solving systems of equations. This session will be recorded, so I will post the link to this out on Canvas, and we'll text that out so that if you weren't able to attend the whole session, you can watch the review. One thing I want to point out is that this study guide, if you access the original study guide and not the one with the solutions, let me go ahead and share this real quick. It has hyperlinks embedded in the document. So if you look at the document, you'll see different links. And so depending on your browser, you might have to allow pop-ups, or you might have to allow Flash to run on your device. But if you select the link, you'll see maybe different tutorials, or you might see some practice questions. So it just kind of depends as you go through the document what you can access. So here we've got some examples. When we get to the two variable equations, you can click the link in the document to practice the solutions online via My Math Lab. So this is kind of like working on your study plan in My Math Lab. And so you can actually use these links to go to those particular types of questions and practice them online. And this document has a ton of examples embedded in it, so it's just how much practice do you need on each topic. Spend that time and check the solutions, and then that will help you gain mastery for the topics. So I'm going to kind of pick and choose some of the examples in this lesson to work out. And if you have any questions, if you're attending tonight, go ahead and either unmute yourself and ask the question, or you can use the chat feature. I'll be checking that throughout tonight and responding to questions there. Okay, so I'm going to go ahead and stop my video because of the device I'm working with. I've got to lay down my laptop so you won't be able to see me on the webcam. So I'm going to go ahead and just stop my video momentarily. And I'll go back to the sharing the screen so I can pull up that study guide. There we go. Okay, so I'm going to show you that the very first page of this just goes through some graphing review, which is helpful so that you can review different types of equations and what graph would come out of those. And then on the next page, you get into the two variable systems. And with this, we're introduced to the different types of solutions that we can get. So with two variables, these are linear functions, and you can either get the two lines to intersect, and that point of intersection is the solution. If you have parallel lines graphed, then we have no solution in common. And then if the lines are the same, whereas they would like lie on top of each other, then we have infinitely many solutions. So you can get different types of solutions depending on the system. So I've got some different links here that you can watch if you need to see some additional like lectures and tutorials. I'm going to go ahead and look at the two variable systems, and let's go ahead and take a look at number 17. So in this system, we have x plus y equals 9, and 2x minus 3y is equal to negative 2. And in this example, we are told to use substitution. So on your quiz, you will be showing the work as you have been doing for all of the other tests for the course. So it's very important to make sure that you do use this particular method. Even if you get the correct answer, you have to have the substitution method demonstrated. So if I'm doing substitution, I need to get a letter alone. And so in this system, I'm just going to go ahead and get x alone. So x would equal 9 minus y. And that's just from subtracting y to the other side. And then I'm going to plug this into the second equation, 2x minus 3y equals negative 2. And I can substitute x with 9 minus y. So that becomes 2 times 9 minus y minus 3y equals negative 2. And now I'm going to distribute to clear parentheses. So I have 18 minus 2y minus 3y equals negative 2. And then when we total up the y's, we have 18 and negative 2y take away 3y is negative 5y equals negative 2. And now I'm going to subtract 18 to isolate the y. So negative 5y equals negative 20. When we do negative 2, take away 18. And then we divide by negative 5 and we get y is equal to 4. Since we did find a solution for y, then we know that these two lines do intersect and the ordered pair has the y coordinate of 4. So now I need to know what the x coordinate is. So I'm going to just back substitute into that very first step where I got x alone. So x equals 9 minus y, or 9 minus 4. So x would be 5. So the solution as an ordered pair is 5, 4. You can check all of your answers on this test by plugging in the ordered pair. You do have to check it in both of the equations though. So if I check this on the first line, 5, 4, 5 plus 4 equals 9. So it does work out in that first equation. And then in the second equation, 2 times 5 minus 3 times 4, that would be 10 minus 12, and that does equal negative 2. So it's very simple to check answers. You just have to plug them back in. Okay, so there's an example of using the substitution method. Again, I said it's really important on this quiz. You're graded on your process more than anything. So if the question says to use substitution, make sure that that is the method that you use. Don't do the addition method. Any questions on that process? Okay. Let's go ahead and take a look at 23 just so we can see what happens in one of those special cases where letters cancel out. So question 23, we have x plus y equals 3, and we have y equals 4 minus x. Again, I'm using that substitution method. Now in this example, I already know y. Y is already isolated. So I'm going to back substitute that into that top equation. So x plus y becomes x plus the group 4 minus x, and then that's equal to 3. Since there isn't a number in front of that parentheses, I'm just distributing a 1. I can remove that. So I have x plus 4 minus x equals 3. And then I'm going to total up my like terms, and you'll notice that the x's, x minus x, cancels. And so you're left with a positive 4 equals a 3. Since this is not a true answer, 4 does not equal 3, this is a case of no solution. So this system would be parallel lines. They have no points of intersection in common. So if your letters cancel and the result is two numbers that aren't the same, that's a system with no solutions. Okay, I'm going to move on in the study guide to 3 variable equations. So you can see you've got a lot of examples here, as much as you need to practice. Now with 3 variable equations, this occurs when we have not lines, but planes in 3 dimensions that are intersecting. And so you can get one solution where all of the planes intersect in what's called an ordered triple. You can still get no solution. And there's a couple of ways that that can happen in 3 dimensions, or you can get infinitely many solutions. So those answers can still occur. So with 3 variable equations, the process that we need to use here is elimination. And so you do have some examples, I think, here going back where you use the elimination method for 2 variable equations. It's the same process for the 3 variable equations, it just takes a little bit more time. So I'm going to demonstrate this elimination method with example 1. And in example 1, we have the system x plus y plus z equals 2, 6x minus 4y plus 5z equals 31, and 5x plus 2y plus 2z equals 13. So our goal here is to find the ordered triple x, y, z, where all three of these planes intersect. So the first step that I demonstrated, if you watched my lesson videos on Canvas, I have a really prescribed process where I take the first two equations, I stack the first two, and I eliminate x. Although you don't have to do that, you could always eliminate y or z if that's easier. But then when I go back with the next step, I stack the second two equations, and I have to eliminate the same letter. So if you got rid of y, then you'd have to get rid of y again. So I just always eliminate x in the first step. So first step, x plus y plus z equals 2, and 6x minus 4y plus 5z equals 31. So I stack the first two equations. I'm going to eliminate x. And so I look at my coefficients, and I need to multiply the top row by a -6 because the bottom equation has a positive 6x, so I need opposite signs. So I'm going to rewrite and multiply -6 all the way through that equation. So -6x minus 6y minus 6z equals -12. And then I have positive 6x minus 4y plus 5z equals 31. So when I add that system together, the x's cancel, and I get -10y minus 1z equals -12 plus 31 is positive 19. Okay? So now I'm going to go back and grab the second two equations. I'm going to stack those. So 6x minus 4y plus 5z equals 31, and 5x plus 2y plus 2z equals 13. Again, you have to eliminate the same letter. So I'm going to eliminate x again. I have a 6x and a 5x. So if I switch the coefficients, where I do 5 times the top row, 6 times the bottom row, I will get a 30x for both of the x's, but one of them has to be negative. So I'm going to do 5 times the top and -6 times the bottom. So as I distribute 5 across the first row, I get 30x minus 20y plus 25z equals 155. Scoot that over a little bit. And then when I multiply -6 on the second row, I get -30x minus 12y minus 12z equals -78. And then I'm going to add these equations together. The x's cancel. I get -32y plus 13z equals 77. Okay, so again, with the three variable systems with elimination, I stack the first two, eliminate x, stack the last two, eliminate x, and now we're going to take these answers, which are two variables, and we're going to do elimination on these two equations. So I'm going to go ahead and just write them together, and then I'll figure out what letter do I want to cancel. So it's really your choice here, whatever looks easiest. So now that I've got those written together, it looks to me like the z is going to be easy to cancel because I have 13z and I have -1z. So if I multiply 13 on the top, then I'll get a -13z that will cancel. So let me go ahead and multiply 13 across the top equation, and that gives me -130y minus 13z equals 247. And then the second equation doesn't change. And then I'm going to add these equations together. So -130y minus 32y is -162y. And the -13z and positive 13z cancel. And on the equals, 247 plus 77 equals 324. So then I'm going to divide by -162, and I get y equals -2. So I've made some progress. I've got one solution. So what we do with this is we back up just a little bit. We're going to go back into the YZ equations and plug in this answer. Okay, so I'm just going to choose that top equation, negative 10y, so that would be negative 10 times negative 2 minus z equals 19. So I get positive 20 minus z equals 19, and then subtract 20, so negative z equals negative 1, and so z is 1. So there's my second solution. So I've got y is negative 2, z is 1. We're going to go back to the very original system, pick one of those three equations. It will work in all three. I'm going to just take that top one because it's just x plus y plus z. It's pretty simple. So x plus y plus z equals 2. So x plus negative 2, and then z was 1, so plus 1 equals 2. So negative 2 plus 1 is negative 1, so x minus 1 equals 2. Add 1, and x is 3. So we've got our solution 3, comma, negative 2, 1. It's always alphabetical order when you write it in the ordered triple. Okay, so I'll zoom back out here. So stack the first two, eliminate x. Stack the last two, eliminate x. Take the answers, do two variable elimination, and then you're going to just do back substitution until you get the final result. Any questions so far? We've covered solving by substitution and solving by elimination with three variables. Remember, you can also use the chat if you want to type in questions as we go through. Okay, all right, so then we learned another way to solve, and it was using matrices. So in your study guide, you'll see some notes about matrices. You can watch some videos about solving with matrices, and there's some good examples about finding the order of a matrix. The order of a matrix is always rows by columns. So in this example 1, I've got 1, 2, 3 rows, row 1, row 2, row 3, so it's 3 rows, and I've got 2 columns, so this would be a 3 by 2 matrix. The next example down beneath it has just 1 row, and it has 1, 2, 3, 4 columns, so this would be a 1 by 4 matrix. If we look over across at example 2, it's got row 1, row 2, row 3, row 4. So it's a 4 row by 1 column matrix, 4 by 1. And example 4 just has one number inside of the matrix, and so it's a 1 row by 1 column, a 1 by 1. That's really helpful to know the dimensions and order of your matrix when you do some matrix operations like multiplication. Okay, so then you have some practice for writing just an augmented matrix, but I'm just going to go ahead and go through a solution where we find the solution using row operations on a matrix. So on the next page, let's go ahead and just look at example 1. So here we have the system negative x minus 5y minus 5z equals 2. Okay, so I'm going to write the augmented matrix for that row. So it would be negative 1, negative 5, negative 5, vertical line where the equals goes, and then the 2. So that's row 1. Now, row 2 is 4x minus 5y plus 4z equals 19. So that would be 4, negative 5, 4, 19. And then row 3 is x plus 5y minus z equals negative 20. So 1, 5, negative 1, and negative 20. So this is called the augmented matrix. It's where you just get rid of all the variables and you put all the coefficients in the matrix. Now our goal is to get the matrix in what's called row echelon form, and that's where we have ones going diagonally and the bottom left corners are all zeros. So all the other positions are numbers. It doesn't matter what those numbers are, but our goal is to get it set up with the ones going diagonally. And when I do this, my process is I fix column 1, and then I fix column 2, and then I fix column 3. So going back to my augmented matrix, notice that in column 1, we have a -1 in that top left corner, and we want that to be a +1. So one way to change that is just through multiplication. And so my row operation would be to multiply by the reciprocal of the number in that position. So the reciprocal of -1 is -1. And so if I multiply straight across, I'm just going to say that my row operation is -1 times row 1. So my new matrix would be on the top row, +1, +5, +5, -2. And I'm going to copy down row 2 and row 3 because I'm not changing those yet. Okay. All right, so I fixed that top left position. You always get the 1 first. Now you get the zeros beneath it. And the way we get the zeros is we multiply by the opposite sign of the number and add it together. So in row 2, we have a 4. So I'm going to go up and I'm going to multiply -4 times row 1 because that has the 1 in it. And I'm going to add it to row 2. And then in the same step, in that bottom position, there's a 1. So I want to do -1 times row 1 and add it to row 3. So we're just taking the opposite sign of that number, going up to that top position and multiplying that row by that opposite sign number. So I can do this in one step. I'm going to write out the operations here. So let's first do row 2. -4 times row 1. So let's go ahead and do -4 times row 1 and write out what those numbers would be. That would be -4, -20, -20, and 8. And I'm adding that to row 2. So row 2 is 4, -5, 4, and 19. So when I add these together, I get 0, -25, -16, and 8 plus 19 is 27. So these are my new numbers for row 2. Now I'm going to do -1 times row 1 and add it to row 3. So going back to row 1, let's multiply by -1. And so those numbers would be -1, -5, -5, and 2. And I want to add these to row 3. So row 3 is 1, 5, -1, and -20. Add this straight down and you get 0, 0, -6, and -18. So these are the new numbers for row 3. So update the matrix. So row 1 stays 1, 5, 5, -2. Row 2 is now 0, -25, -16, and 27. And row 3 is now 0, 0, -6, and -18. So when you check the progress here, you fixed row 1, you got the 1, the 0, and the 0. And so now we're going to move on. We fixed column 1. Now we're going to move on to column 2. Now column 2 has a 5, and then a -25, and then a 0. You always get the 1 first, so we want the 1 in that row 2 position. So to change the -25 to a 1, we multiply by the reciprocal, and that's it. So the reciprocal of -25 is -1 over 25, and we're going to multiply that by row 2 straight across. So let's update the matrix again. So row 1 stays the same, and row 3 stays the same, and row 2 I'm multiplying by -1 over 25. So -1 over 25 times 0 is 0. -1 over 25 times -25 is a 1. -1 over 25 times -16 is +16 over 25. And then -1 over 25 times 27 is -27 over 25. So there's my updated matrix. Still working on column 2. Notice that I do have the 0 beneath it, so I do not have to do that step where I change the 0. So I can go on now to column 3. So in column 3, we just need that third row. We need that -6 to turn into a 1. So I can fix that by multiplying row 3 by the reciprocal of -6, which would be -1/6. So update the matrix once more. So copying down row 1 and row 2, and then row 3, we have -1/6 times 0 is 0, -1/6 times 0 is 0, -1/6 times -6 is 1, and then -1/6 times -18 is +3. So this is now in row echelon form because we've got the ones going diagonally, we got that bottom left corner zeroed out. So this gives us an automatic solution in row 3. It tells us that z is 3 because the x and the y are zeroed out. And then we can back substitute that into row 2, which says 0x, it says 1y plus 16/25 z equals -27/25. So I'm going to substitute z into this equation. So y plus 16/25 times 3 equals -27/25. So then multiply. 16 times 3 is 48. So we have 48/25. Y plus 48/25 equals -27/25. And then we're going to subtract 48/25 over. And so that gives us a whole number, -3, when we do that subtraction. So I've got two solutions. And now I can back substitute y and z into row 1. And row 1 says x plus 5y plus 5z equals -2. So substitution gives us x plus 5 times -3 plus 5 times +3 equals -2. So x minus 15 plus 15 equals -2. The 15s cancel, and so x equals -2. So the ordered triple x, y, z is -2, -3, 3. And going back through how I wrote out my steps, I did label row operations. So always show what you're doing. That's part of showing your work, and then rewriting those matrices as you go. So be prepared for solving a system using matrix operations. For those who are attending tonight, does anybody have any questions on the steps, or does anybody need clarification? Okay, so let's move on to matrix operations. And so with matrices, you can add and subtract. You can do a form of multiplication. And so we've got some examples here where we can do some of those operations. So what I've got on this study guide is you have a bunch of different matrices that are referenced here, and then you have some different steps. I'm actually going to go to I'm going to move on to question 21. Yeah, the next page. I'll go back and do the addition, but here on this next set of questions, we're just finding the product of the matrices. And finding the product is really strange. Until you practice it and get the hang of it, it's kind of weird. But in order to do the product, we first need to look at the dimensions or the order of the matrix. So it's rows by columns. And then we have the second one, rows by columns. In order for you to be able to find the product, the number of columns in the first matrix has to match the number of rows in the second matrix. Okay, so let's go ahead and just see with these examples if it's even possible. So in my first example, 21, notice that we have 2 rows, 1, 2, 3 columns. So that's a 2 by 3. In the next matrix, it has 1, 2, 3 rows by 1 column. So notice that the inside numbers, when we write the orders together, they match. So the columns of the first matrix matches the rows of the second, so we can perform the product. And the product is going to generate a 2 by 1. So it's like the inside dimensions cancel and the first number, last number go together, and that's going to give you the dimensions of your new matrix. I'll go back and solve that, but let's go ahead and look at some of these other ones. Like 23, we have a 2 row by 2 column, and then we have a 2 row, that's a 3 row by 2 column and a 2 row by 2 column. So since those inside numbers match, we can do it, and the answer is going to be a 3 by 2 matrix. So that one's one we can do as well. Let's look at 25. In this example, we have 3 rows by 1 column, and then the next matrix that we're multiplying by has 2 rows by 3 columns. Since the inside dimensions don't match, the number of columns of the first matrix is not the same as the number of rows in the second. This one is not possible. Okay, so if those inside numbers are different, you can't perform the product. So now that we've seen some examples and seen how we can figure out if the product is possible or not, let's go ahead and actually show how to do the product. And I'll show this with this first one here. So on 21, we have a 2 by 3 and a 3 by 1. So we know that the answer is going to be a 2 row by 1 column. So that's really important because you could set up the answer with 2 rows and 1 column. So you already know how to fill it in. You might need more space to show the work, but that's the idea there. It's just one position here. So the way that we multiply is we're going to start with, let me erase some of this stuff here. Start with the top left number, okay? And we have a -1, and we're going to multiply it by that first position in the second matrix, which is a 6. So I have -1 times 6 plus, and I move on to the second number that is in that first row, and I multiply that by the second number in that other matrix. So I have 0 times -4. And then I have the third numbers multiplied together, so 7 times 1. So -1 times 6 plus 0 times -4 plus 7 times 1. And that result is going to give me that first number, top row, top column. So that's going to equal -6 plus 0 plus 7. So that's going to equal a +1. Okay, now we're going to move on to the second row. So the sequence of steps is the same, but we now have 3 times the first number, 6, plus -5 times the second number, -4, plus 2 times the third number, 1. Okay, so that's 18 plus 20 plus 2, and that equals 40. So I have a 2 by 1 matrix, and the numbers are 1 and 40. Let's go ahead and look at another example like number 23, just for one example that gives a longer matrix, I guess. So we have a 3 row by 2 column and a 2 row by 2 column. And so since the inside number dimensions match, then we can do it, and the answer is going to be a 3 by 2. So it means I'm going to have 3 rows, 2 columns. Okay, so as we do this product, we start with row 1 in the first matrix. Okay, so row 1, the first number is a -2. So I'm going to do -2 times 3 plus 4 times -1. So notice how I did row 1 times column 1. And the positions should always have a number that it lines up with. Now, to get that second position over here, I've got to distribute to column 2. So now I'm going to do -2 times -6 plus 4 times 4. Okay. All right, so let's go ahead and fill in those first 2 positions in row 1. So I'd have -6 minus 4, so that would be or hold on, negative 6 plus negative 4, yep, so that would be negative 10. And then I have 12 plus 16, so that second position would be 28. So top row is negative 10, 28 in that 3 by 2 matrix. Okay, so now we're moving on to row 2 in the first matrix. So I'm going to do row 2 by column 1, and then I'm going to do row 2 by column 2. So it goes 5 times 3 plus 1 times negative 1. And then I do row 2 times column 2. So 5 times negative 6 plus 1 times 4. So first positions go together, second positions go together. Okay, so that would be 15 minus 1, so 14, and negative 30 plus 4, so negative 26. So 14, negative 26 for row 2. Okay, and now we go ahead and apply row 3 in the first matrix by column 1, and then row 3 by column 2. So that would be negative 1 times 3 plus negative 3 times negative 1. And then we have negative 1 times negative 6 plus negative 3 times 4. So that would be negative 3 plus 3, so that would be a 0. And then positive 6 minus 12 would be a negative 6. So we've got our 3 row by 2 column matrix finished. Let me show you what happens if you try to do this with one of these that's not possible. So we said that number 25 is not possible because we have a 3 by 1 matrix and a 2 by 3, so that's not possible. So let's see if you even tried to set this up. Okay, so we would first do row 1 by column 1, and notice that you kind of get stuck here because you would start by doing 1 times negative 6 plus, but then you don't have a second position to multiply by the 0, so that's why it's not possible. You're missing that second number in the row to match it up with the second number in the column. So you've got to have 2 numbers in the rows if you've got 2 numbers in the columns. So that's why that will not work. Okay, so you got lots of practice there with products. Adding and subtracting, that's really self-explanatory. You can even multiply a matrix by a number. So, if I do 2 times matrix A, then I'm multiplying all of the numbers by 2. You're just doubling the whole matrix. If you add 2 matrices together, you're just adding all the numbers in their positions together. So like matrix A plus matrix B, then I would add 1 plus negative 3, so you're doing the top left numbers. 4 plus 2, so that's your row 2, column 1 numbers. And then we have 2 plus 5 is 7. 3 plus negative 1 is 2. So your just corresponding positions have to add together. So obviously when you add matrices, they have to be the same size, the same dimensions, okay? So you can do a 2 by 2 and a 2 by 2 because everything has a match when you add it up. But you couldn't do a 2 by 2 and a 3 by 3 because you wouldn't have matching numbers and positions. Okay. All right, so study those matrix operations if you need more practice. The end of this lesson deals with linear programming, and I know that that's where lots of questions come from because, boy, these problems can be quite intensive to set up. Let's go ahead and take a look at one of our examples that we've got listed here. So I'm going to work out this first linear programming question that's towards the end of the study guide. I'm going to try to fit in 2 examples just so you can kind of see a difference where one is greater than and one might be less than. Okay, so Waterbrook Farm includes 240 acres of cropland, and the farm owner wants to plant this acreage in both corn and soybeans. And the profit per acre in corn production is $325, and in soybeans is $180. A total of 320 hours of labor is available, And each acre of corn requires 2 hours of labor, and each acre of soybeans requires 1 hour of labor. So how should we divide the land between these 2 acres of crops, corn and soybeans, to yield maximum profit? And what is that maximum profit? So when you're setting up these problems, the first step is to define your variables, like what is X and what is Y, or if you want to do like C for corn and S for soybeans, something like that. Look at the very end of the problem because it tells you what you're looking for. So it says, how should the land be divided between corn and soybeans? So I'm going to let X be acres of corn, and I'm going to let Y be acres of soybean. And that's just going to help me when I set up the constraints of the equations. So one constraint deals with acreage. So we're looking for like limitations in the problem. And it says that the farm has 240 acres of cropland. So X acres of corn plus Y acres of soybean cannot be more than 240. So it's got to be less than 240 acres together. So I've got my acreage constraint. Now, if I keep reading, it says that we have profit. So that's a totally different thing. That's going to be used at the very end of the question, but I do need to set up my profit function. And this is just used at the end to determine the maximum profit. So it's 325 for corn, so that would be 325x plus 180 soybeans, so plus 180y is going to give me my profit. So I'm going to come back to that at the end. So I'm just kind of reading through and just marking off what I've used so far, making sure I'm addressing everything. And so now I get to some other numbers, like 320 hours of labor is available, and labor is split up into corn labor, soybeans labor. So we have another constraint, and it's labor. 2 hours per acre of corn, so that would 2 would match up with the X. Soybeans, 1 hour of labor, so plus 1 for each Y, and it's limited to 320 total, so less than or equal to 320 hours total. I think we've got everything. We always have the constraints, X must be greater or equal to 0, Y must be greater than or equal to 0. Hopefully you've picked that up because you can't have negative acres, you can't have negative dollars, all that is embedded in that. So we're always dealing with that first quadrant. So from here we want to graph this, okay? So we want to graph the constraints in the first quadrant. And what we're looking for is we do have to shade. Okay, so that's a big deal because this gives us the region of solutions. So I'm going to set up, to the best of my ability, this graph. Looks better on my paper where I wrote it out. It's kind of hard to do it freehand. So we got this first quadrant. And the best way to do these is by finding intercepts. Okay, so that's where we take X plus Y equals 240. So if we let Y be 0, X is 240. And if we let X be 0, Y is 240. So it's very simple to get the intercepts to plot with that equation. And then for the second one, 2X plus Y equals 320. Well, if we let Y be 0, we have 2X equals 320. So X is 320 divided by 2. So 320 divided by 2 is 160. And then if we let X be 0, we just get Y equals 320. So find your intercepts, and that lets you pick an appropriate scale for graphing by hand on your system. So I've got some pretty large numbers, so I did a scale where I went up by 60s on my axis. So when you're doing your quiz, you might want some graphing paper or like rulers or something like that to help you out, so you can see how to plot this. So I'm using the same scale on the y-axis as I did with the x-axis, and so now I'm going to graph my intercepts. And so the first line crosses at 240 on X and 240 on Y. The second line crosses at 160 on X and 320 on Y. Do my best to connect those. So we can see a point here. And then shading is really important. So both of these inequalities were less than the lines, and so that's shading below each line. So we end up going underneath each inequality, and it pushes the shading to this objective region here. So it's like this quadrilateral shape. And so then we want to find the vertices of this, which is all of the corners. Okay, so we obviously have 0, 0, which wouldn't be used to find a profit. Okay, so I'm not even going to plug that in. And then we have a point up here at 0, 240. And then we have a point over here at 160, 0. And then we always get this question where the two functions intersect each other. And so this is a great application of solving systems of equations. I know a lot of you guys have graphing calculators and you can like plug it in and find the point of intersection with technology, but we've learned how to do that algebraically. So look at the two lines that are intersecting. Let's go ahead and stack these two equations. Okay, so I had x plus y equals 240. You can get rid of the inequality. 2x plus y equals 320. So I stack the two lines. And I'm going to use the elimination method. So the easiest letter to cancel would be the y, but I need one of them to be negative because I got a positive y and a positive y. So I'm just going to do a negative all the way across that bottom row. And then I'm going to add the system together. So 1x plus negative 2x is negative 1x. The y's cancel. 240 plus negative 320. Do that a little different here. So 240 plus negative 320 is negative 80. And so when you divide by negative 1, you get x is positive 80. And we just back substitute that into one of those original equations. I'm going to use the first one, x plus y equals 240. So 80 plus y equals 240. And so 240 minus 80 gives us the solution for y. Y is 160. So that mystery point of intersection, that vertex is 80, 160. Okay? And so what we do with this now is we use that profit function and we test the corners of the region to see which one gives us the maximum profit. Okay, so remember that in the very beginning, our profit function was 325x plus 180y. So I have 325x plus 180y. And we're going to test our ordered pairs. We don't do the 0, 0, but you can test the others. So let's do 0, 240. So that would be 325 times 0 plus 180 times 240. And that would give us a profit of $43,200. And then our other ordered pair was 120, 0. Is that right? No, 160, 0. Make sure. Yeah, that should be 160, 0. So that would be 325 times 160 plus 180 times 0. So 325 times 160 is 52,000 for the profit. And then our final vertex that we found from the intersection, which is usually our solution, is 80, 160. So plugging that into the profit function, we have 325 times 80 plus 180 times 160, and that's going to yield a profit of 54,800. And since it said what's the maximum profit, we found it there. That's the biggest number. So our max profit that we can achieve is 54,800 if we farm 80 acres of corn and 160 acres of soybeans. So being able to interpret that ordered pair at the end is also really important. Okay, so that's how linear programming is used in business type situations to help when we've got multiple variables and multiple constraints, we want to find a way to maximize the situation. Okay, so looking through, I've zoomed out on that. If you have a question, let me know. Right now I'm going to fit in, we've got 10 minutes. I'm going to do one more example. And then there's more in this that you can practice. Okay, all right, so let's go ahead and look at the second example. So our second example is a manufacturing question. Toys A Go makes toys at Plant A and Plant B. Plant A needs to make a minimum of 1,000 toy dump trucks and fire engines. Plant B has to make a minimum of 80 toy dump trucks and fire engines. And Plant A can make 10 toy dump trucks and 5 toy fire engines per hour. And Plant B can produce 5 toy dump trucks and 15 toy fire engines per hour. It costs $30 an hour to produce toy dump trucks and $35 per hour to operate and produce toy fire engines. How many hours should be spent on each toy in order to minimize cost, and what is the minimum cost? What throws people off with this type of question, I can tell you right now, is like you've got Plant A and Plant B, and then you've got like dump trucks and fire engines. So like, what are your variables going to be? Is X going to be Plant A and Y is Plant B? Or is X going to be dump trucks and Y is fire engines? So the strategy is always focus on that ending sentence, find that question word, and it tells you what your variables are. So it says, how many hours should be spent on each toy? Okay, so that tells me that my variables have to be defined by the different toys. So X is number, I'm just going to do the first one, dump trucks. And Y is number of fire engines. Okay, so that's a really helpful strategy to avoid that confusion. And then we go from there and we do constraints, and then we do our profit function, but in this one, it's minimizing cost. So my cost function, look for dollar signs and then match them up with your variables. It costs $30 per hour for the toy dump trucks. That's why we do the variables first, because every time I see dump truck, that's an X. So I'm going to do 30X plus 35Y. So there's my cost function that I'm going to use at the end after I get the vertices of my region. Okay, now let's go ahead and list all of the constraints, limitations, and so on and so forth. And we know X is greater than or equal to 0, and Y is always greater or equal to 0. So going back and reading the first couple of sentences, I see that it's divided up into Plant A and Plant B, and they've got different constraints referencing those. So let's do a constraint about Plant A. So it says at Plant A, Plant A needs to make a minimum of 1,000 dump trucks, so that would be 1,000X. Well, hold on. 1,000 toy dump trucks and fire engines. I had to keep reading that. That's actually 1,000 toys, so not just for the first one. And Plant B needs to make a minimum of 800 toys. Okay, so those are like your limits right there. Plant A can make 10 toy dump trucks, so 10 goes with X, and 5 fire engines, 5 goes with Y per hour. So there's my equation for Plant A. Plant A is 10X plus 5Y, and then look at your limit for Plant A. They want 1,000 toys, and it's a minimum, so you want it to be greater or equal to 1,000 toys. And then Plant B can do 5 toy dump trucks, so that would be 5X plus 15 fire engines, so 15Y. And then your limit for Plant B, minimum of 800 toys, so greater or equal to 800. Okay, so that's my Plant B. And I think we got everything in there now. So we got our constraints that we want to now graph. We got our cost function. So setting up the first quadrant again, and let's go back and find my intercepts. So for the first equation, x-intercept would be 1,000 divided by 10, which is 100, and the y-intercept would be 1,000 divided by 5, which is 200. And again, that just comes from where you like plug in 0 for x, so 10x is gone. Plug in 0 for y, 5y is gone, and it's just a shortcut there. And then for the second equation, x would be 800 divided by 5, which is 160, and y would be 800 divided by 15, and that's 160 again. No, it's not. Making sure I got the right coefficients there, because that, on my notes, I think I wrote it down the wrong number there. Okay, so 800 divided by 15 is 53.3 repeating. Like that. So I'm going to go ahead and write out several of those numbers there. But for graphing, you can estimate where that intercept would lie. I don't know why I had that off. I want to make sure that that's right, but it looks, just solving in my notes, I just had an error there, I'm sure. So my scale that I'm going to use, I went up by 20s. I didn't have to go up. I could have changed that, but let's go ahead and just use that. So going up by 20s. Probably because I thought that that one intercept was so high. And the other one, same scale. Okay. And graphing that first line, it has an intercept. X is 100 and Y is 200. Okay, so we graph that first line, and then X is 160 and Y is 53.3. So connecting those. Now in this, oh, this is just bothering me because that one that one intercept that doesn't match what I got there. I just want to double check that. Make sure that my numbers were right for plant B again. So plant B has 5 and 15. And plant B was 800. Yep. Okay. So how do we shade? This one is shading greater than each line. So like at each line we're going out, and then this line we're going out. So the intersecting region is out here. And so this region is bounded by, it looks like, 3 corners. Okay, so we got this one corner that's up there, and that point is the 0, 200. So we have a vertex at 0, 200, and then we have another point down here at 160, 0. And then we have this intersection region again. So usually that's going to be the solution that will work, but we need to solve the system where we stack these two equations and find their point of intersection. So I'm going to go ahead and write the 10x plus 5y equals 1,000. 5x plus 15y equals 800, and using that elimination method, let's see what we can cancel here. Looks like it would be easiest to cancel the x, although you could multiply by 3 to cancel the y, so pretty simple. I'm going to multiply -2 by the bottom row. So I have 10x plus 5y equals 1,000, and then the bottom row is -10x minus 30y equals -2 times 800, which is -1,600. Add those together, the x's cancel. 5 plus -30 is -25y, and 1,000 minus 1,600 is -600. And then so we divide and we get y is 24. And then back substitute, I'm going to just use that top equation, 10 times x plus 5 times 24 equals 1,000. So 10x plus 120 equals 1,000. You're going to subtract the 120. So 10x equals 880, and 880 divided by 10 is 88. So the point of intersection is 8824. And now that we've got our 3 vertices for that region, we can use that cost function to see, and remember this time we're wanting to minimize the cost, so we're looking for that lowest number. Okay, so cost function is 30x plus 35y. So 30x plus 35y will test the vertex 0 to 100. And so 30 times 0 plus 35 times 200 is a cost of $7,000. And then we have 160, 0. And so 30 times 160 plus 35 times 0, and that gives us a cost of 4,800. And then the point of intersection we got was 88, 24, and so 30 times 88 plus 35 times 24 is 3,480. And so our minimum cost is 3,480, and that's generated if we make 88 dump trucks and 24 fire engines. Okay, so I'll zoom back out on that. So that point of intersection that I had, that intercept, it was wrong in my solution, so I'll have to correct that, but it didn't affect, you know, the final answer, so that's why I didn't catch it earlier. But if you look at these two, one of them was a maximum profit, and then here we have a minimum cost. And so it's all based on those inequalities, like which direction you're shading and how it's going to end up being set up. You could see that with these linear programming questions, usually that point of intersection is the one that generates either the maximum or the minimum that we're looking for. So you've got some other examples that you can try. To fully prepare for this quiz, you need to be able to do all different problem types on this study guide without looking at the notes to help you out. So you might have to work this out a few times to gain mastery. But I did record this session, so I will post the link to the recording so that those of you who weren't here the whole time can watch that and maybe kind of slow it down and pause it. That might help you too. Okay, so I'm done with the review. We did pretty good. We got all those questions done in an hour. I'm going to go ahead and stop recording, and if you do have any questions, let me know before I close out. Let me go ahead and stop recording real quick.